let me just get this thing settled down and then we begin. Okay. Um, and then something I created a pull request on the this one on the
Yes,
repo that
yes,
yeah
I saw that one. So I said
yeah
before I comment, let me check. I think I've checked and I've replied now. I think things are okay.
all right.
Yeah, I've just commented now. Can I merge maybe the pool?
So, I
Okay,
mean,
okay,
since it is your repo, I didn't want to commit directly to the to the main branch.
okay.
Yeah. All right. So, I've also created this one. So, I think we can actually maybe if what's the name again? Ahmed, if you would like to start the recording, I think that'll be okay. I would like I think we can start from now.
Okay, okay, sure, sure. Okay, let's continue.
All right. Okay. So like we discussed the last time, we mentioned that the linked list is essentially something that looks um okay. Probably I think I lost it. Anyway, um, the linked list that we are going to build, we mentioned that it's going to be something similar to this, and so let's go through what we are going to do today. Essentially, what we are going to do is work with linked lists, the implementation side of it. So we are going to see how to build a linked lists and how to insert nodes into it at the beginning or at the end or somewhere within the linked list, as well as we're going to see how to search or delete a node. And I put this together because for us to delete a node, we have to find it. Okay, so the searching and then the deleting, I'll put that into one, but essentially you get the idea of what is happening. Then, as a final thing, we are going to learn how to reverse a single linked list. Yeah, a single linked list. So the solutions over here would try to be in a simplest form, but then there's probably going to be a different way to do it, or maybe a much more efficient way to do it. But here I'll try to keep it, let's say, as simple as possible, whilst also keeping the like keeping it still usable and still efficient to some level. Okay, so without much ado, what we will start with is a quick introduction to what we are going to be building. So the first thing that we will do is we will build out our node structure, which is going to be this and the linked list structure. We would add a few things and a few macros that will be used to cover a few things. So we would also have a function called init, which is going to handle the initialization of the linked lists for us. Okay, so that's going to be the initial part of what we are going to do. So we will create these structures and these functions that are going to be used to do these things. Then we are going to have some few functions that we will create to insert into the linked list. Here I call them append and then the push. So the push here is going to push at the beginning and then append will insert at the end of the linked list. All right. So that's what we are going to be doing over here. Then we're also going to create some functions that are going to insert somewhere within there. So I'll call that insert just for that sake. Okay, so the push is going to push at the beginning, the append inserts at the end, and then let's say the insert, probably let's just call it insert art just to make it easier to maybe work with. Okay, so these things over here, and the last time we saw that, oops, give me 1 second, sorry.
Maxwell, and that wasn't. You won't blow on the ears or something.
No, no, he's coming. He's coming.
I, yeah,
Welcome, Patrick.
Max.
Yeah.
uh,
Sorry guys, I asked that I be excused a little bit. Sorry if you didn't catch that. Yeah, I received.
You won't blow on a yes or something.
All right. So sorry about that. Let's get back
Okay.
to uh, the thing. All right. So we talked about the fact that a linked list is a non-contiguous data structure, unlike the array, which is having contiguous memory allocated to it, meaning that the memory that we have are side by side or adjacent. Or let's just say that the block of memory that we receive is um, in, let's say, counting form, right? So from one, we move to two, three, and in that order. But when we talk about linked list, the data or the memory that we allocated is scattered across the memory. Okay. So now the thing here is that I've also drawn out some linked lists and how we are going to be working with it. So in this linked list here, we are going to have the head and the tail nodes. And the reason why we are going to do this is so that, for example, when we are appending into our linked list, we are going to not, let's say, incur a lot of costs when it comes to just inserting at the beginning or inserting at the tail. But then if you're inserting within it or inserting somewhere within the list, then we can just agree that we are going to have an O of n, meaning that we would have to traverse and insert over there. So we are just trying to be efficient as possible everywhere we can, and then only use, um, let's say, the O of n every time that we can't have a constant operation. So the O of n just means that whenever we are going to insert into a linked list, it's going to be based on the size of the linked list at any particular point in time. So that is why we are keeping the tail node, so that in case we need to insert at the end, we insert over there. All right. So that is what is going to happen. And we are also going to have a few functions that are going to handle the popping of the linked list, right? As in taking information out of there. So I have um, laid out most of the things that we are going to do over here, and you can check them out. All right, so once we are building it, I'll be referring us back to these things, and then we'll be seeing how it's going. When we are inserting at the beginning of the linked list, or when we are inserting at the end, a few things that I've just written over here. Okay, so because of, let's say, time, we'll be discussing it once I build it. And if there are any questions, you can as well raise your hands, and then we would discuss that real quick, then move forward from that side. Okay, so now what I'll do is I'll bring up my terminal, and then the first thing we'll do is we will create our header file, and I'll call it lists.h. So we will try to protect our header file. Oops, so we will say that if this over here is not defined yet, then I would like to define the lists header file. So we'll create the structure based on what we said we would do. So that's going to be the node S, just to mean that there's a node structure. And then we are going to put the things that we need to put over the fields or the members. And here we are only keeping two members, the data portion, and then a structure, as in a pointer to the next node structure. Okay, so I asked that we look up how structures work and things like that because of the things that we are trying to do today. Okay, so struct node s and then pointer to the data. It could have been more. We could have also stored a character array or a string and many things like that. But to keep it simple, we'll just store this one over here. Then we'll give it a name as a node T, just to say that there's a node type. Then for the next one, we're going to create a struct for the linked list. So there's going to be list S, right? Just to say there's a list structure. Then it's also going to be the same thing. But here, like I said, we are going to keep the head and the tail. So here we are keeping the head and the tail. So this way we are able to handle when we are at the beginning and when we are at the end. And this is going to be very much useful when we even do stacks and queues, and particularly, let's say, when we are dealing with doubly linked lists, right? So with doubly linked lists, we know that we can traverse forward or backwards, which I'll hold on to for the moment. Maybe next time, if we get a chance to talk about doubly linked lists, we can talk more about that. So we'll keep the address of the head and then the tail. So let's go ahead and then you say node T, that is what we are trying to keep, that is a head, as well as a node T for the tail. Then another thing that I would like to keep is the size of the linked list at any particular point in time. Okay, so this way we are able to know ahead of time that, okay, well, the linked list at this particular point is this much nodes, or it contains this number of nodes. Okay, so currently we have everything we have on the board in code as well. So the node structure and then the list structure. Okay, so a few things that we can also keep. Um, we can keep function pointers. We can keep basically anything that you would like to keep over here, anything at all that you would want to keep, and also to make things simpler. And then from where I learned it, like they have a very cool thing that they use. If you're not familiar with that, there's a book called Mastering Algorithms with C. They teach very cool things when it comes to data structures. So here, what we are going to do is we're also going to have a function pointer, which is going to point to a user-defined function that is going to be used to remove or clean up nodes as we pop them out or as we delete them. Okay, so I'll explain this as we move forward. So here we are going to create a function pointer, and then I'll call that a cleanup function. What it does is it's going to receive a double pointer. Right. So um, here we are just saying that this function is going to return void, and it's going to receive an argument or a parameter, which is going to be a double pointer. Okay, so I would explain this as we use it. It's basically going to be a function that the user will create that will remove some data or clean up memory. It's going to be using the free function, but then it's going to be wrapped around it, and you talk about why that is the case. Okay, so now the few things that we also have to do is we mentioned that we'll be using the init function, the append, and then the 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 push functions. So let's go ahead and then define those functions as well. So the init function is going to return the newly created linked list. So what we do is we say list t is going to be equal, sorry, list that. And then what we are going to also do is we are going to allow the user to pass in the cleanup function that they have written. Okay, so here we would also say that void like that. Okay, so while we are initializing the linked list, we would ask the user to give us a pointer or the function that they are going to use to create that for us. And before I mess things up, actually, what we should do is that remember that this is supposed to be a function pointer. So I think I would like to poke your minds a little bit. How do you think I should write this um, particular parameter? Is this supposed to be just the way that I did here? Do you think that a function pointer should be written like this? Maybe something like this? Or there's something else that you think I'm missing out here? What do you think it should be?
Mulena. Okay, maybe.
Something. Let's
Okay.
say, yeah, yeah.
Maybe the first thing I would like to say about the void, two asterisks, then cleanup. I would say that is a pointer to a pointer, right?
Yes.
Or it can even say maybe an array of arrays. But if you are to define a function pointer, maybe you can first give the return data type if it's void, then you need to use brackets. So for us, we want to build for cleanup, so it will be into bracket asterisk, then cleanup, then close it, and then again you need to give parameters to specify the parameters for the targeted function.
Right. So something like this. Right. Right.
Yes, but
Okay.
if it's taking in parameters, yes, you can do that.
Yes.
Max,
Yes.
Max.
Yeah, boss.
Yeah. So for the list initialization function, right?
Yes.
So you actually only passed in the what do you call it? The function pointer, right?
Yeah, yeah, yeah.
Uh, So I think wouldn't it be more what do you call it? More efficient and straightforward if you passed in the list to a pointer to the list.
Come again.
I said that wouldn't it be more efficient if you passed in a pointer to the list too?
If I pass a pointer to the list.
No, you see that you see that you pass in what do you call it? A function pointer to the destroy function or the cleanup function.
Yes.
Yes, and I'm asking, wouldn't it be more efficient and straightforward if you passed in the a pointer to the list too?
Okay. So maybe let me like break down how this init function is going to be used here. Okay. So what I'm trying to do is that when the user is calling this init function, that is when the list is being created. Okay.
Yes.
So as you can see on the left side here, right? So when we are going to define the list, we are going to call it in this method or in this way. So list equal to the init method, but then here we are going to pass in the function that's going to do the cleanup or the destroying, right? So at that particular point in time, the list has not yet been created, so I can't pass in a parameter to the list if that's what you are saying.
Well, okay. I think to each with their own implementation because me anytime I'm creating a list initializing function, I pass in the list, right, and then I pass in the cleanup function just like you've done. So I initialize the list and the what do you call it? The passing function. What do you call it? The cleanup function or the destroy function in
Yeah.
at the stage where I'm initializing the list.
Yes, that's the same
So
thing happening here.
what did you say?
Yeah, I'm saying that that's what is going to happen here. Like when we are initializing the list, that's where we are going
Right.
to take this parameter or this
Mm-hmm.
argument. That's how it called. Yeah. So it's at the time that we are creating the lists. Right. So probably here. Right. So um, in this over here, like the detail for the cleanup is not mentioned, but then here's where it will be defined or will be stated. So we are creating a linked list over here. All right. So this is where we are going to pass in. So at the end of this function, the return value is going to be stored inside of the list. So
Yes.
that's what is going to happen. All right.
Right. Right.
Yeah. Okay.
So
So
okay, I think what I actually missed is the return value because when I pass in the what do you call it the pointer to the list, I don't return a value.
okay, okay, I see.
I
All
only
right.
I just return void.
Okay. Yeah. I just wanted to make it look like this. That's all. Yeah. Okay. Well, that's also one way to go about it. Okay. So now we are clear on this particular one, right? For the
Uh,
initializer function. Yeah, something.
Also
Just
teachers.
before you carry on, Max,
Yeah.
uh, maybe you can finish the structure that we were creating, the type def struct list underscore list, and
Yeah. Thank you.
before you, yes.
Yeah, thank you. Missed that. Thanks. Okay. All right. So that's the initializer function that we have here. So the other functions we are going to have is,
Max, I beg, sorry to cut you. This one, you go YouTube.
yes, yes, yes.
Okay, okay. And I'm judging me.
All right. Okay. So the push function. So we have the push function. We also have the append function, and we also would have. I mentioned another function that we'll be using. That's going to be um, the insert at. So currently, I'm just writing out these, and then I'll be putting them correctly. So I like to keep them over here. And then let's also have the pop function, right? So um, the the pop will just do a delete at a particular point. Okay. So let's probably also do delete at. Right. So now, what this function here is going to do, the void, sorry, the push function is to insert at the beginning of the linked list. Okay, and what we are going to do is we're going to insert into the same linked list, so there's no need to return anything, and I wouldn't be returning anything for that. So we are going to receive the list that we want to insert into. So we are going to receive the list. Then we're also going to receive the data that we would like to insert into the linked list. All right. So here we have the list that we want to insert into, and then the data that we are trying to insert into the linked list. So that's what we have here. So the rest is going to also have something similar to that. So the oops, the append is also going to take the lists and then the data. The insert art is going to be a little bit different. All right, so this is going to be lists T like that, the list name, the index which we want to insert at, and then the data. So int data. Okay. So then for the pop, also for this we wouldn't return the value that was popped. We'll just leave it at that. We'll just remove the information. But for the sake of keeping it fine, what we are going to be doing is we are going to be printing out messages when there are errors and other things. There are other ways. Maybe you like to maybe return a specific data code or something, but we wouldn't do that. So the other thing here is also when we are trying to delete something from the linked list, all that we need is the list that we are trying to pop from. Since you're going to be removing from the head of the node or like from the beginning of the linked list, we just need the list we are trying to pop from. Then the delete at is also going to look something similar to the insert at. So it also taking the list that we are trying to pop from, the index we want to pop from, and then the date. Sorry, yeah. So this is going to take in the list and then the index that we are trying to remove from or remove. We could also do it something different that okay, well, we rather want to remove the data and not the from a specific index. Both ways are dependent on how you would like to do that. But for this, we will try to do it with the index instead of the specific data. So this would be for what we have here. All right. So usually, to what I like to do is to have some macros that are going to return the first and then the last element of the linked list, just for the sake of just looking at them to make it easier to work with. So here I'll define a macro called first, and it will take in a list. And what it's going to do is going to just return some data from the list, which is really going to be um, the head, right? And then sorry, the yeah, yeah. So you're just going to take the data from the first or the head node and then just print it out. Okay, so that's what it's going to do for that particular one. And then the same thing is going to be true when we come to the last node. Okay, so also we just say last and then lists, lists, tail, and then the data. Okay, so that's what we are going to have here. And then I'll end our guard. Let's just make it sure that is well. All right, so these are the things that we are going to be using for the function that we are going to be creating at this point. The size over here is going to keep the size of the data, sorry, of the linked list. But I think one thing that I've just left out is the function pointer that I mentioned previously. So here there's a function that we are going to create called free, right? We can also call it cleanup or anything, but I'll just like to call it free because it wraps around the original free function. So that's what's going to have the double pointer in that. So here we are going to use this function to deallocate memory in a way that is going to ensure that we are really deallocating memory and then handling dangling pointers. I wrote a blog about that and I can share that as well when we are done with the video. Okay, so these are what we need for what we're about to do. And for the ease of moving about, I'll create a different window where we are going to be writing the code. Okay, yeah, Samson, I see your hand is raised.
Uh, Maybe just something to point out. Uh,
Yeah,
in your header file,
yes.
your first statement was to gather. Yes, if not defined, maybe you
Oh,
normally
yeah,
write it. Yeah, if not defined, the if
yeah.
and
I,
yes,
I,
yes.
I rather said that. Yeah, I
Okay.
thought I did that. Yeah, thanks, thanks. Yes, great. Okay, so I think we can go ahead and then create our um, files to handle these things over here. So for the function that are going to not do something specific to linked lists, right? Uh, the usual operations that we perform on the linked lists are going to be the push, the append, insert at, the delete, and then the pop, right? But for the free and then the init, they are usually, let's say, miscellaneous functions. So what I'll rather do is I'll put them in a separate file. So the actual operations that we are going to be dealing with are going to be one, two, three, four, five. Right? So that's what I'll put in a single file, and then the init and then the free functions are going to be in a separate function. So here, what I'll do first is I'll create the init function and then the free function. Then we are going to work on the specific ones for the list operations. So here we create a file and then I'll name that um, extras just for that. So here is where we are going to create the files that I just mentioned. So here I will include the list.h. But before anything, I think I forgot to add a few of the header, the libraries that we'll be using. So I'd like to include the stdio.h so that we can be printing error messages, as well as the standard lib, so we can be using the malloc and then some exit code failures when we fail to like handle a few things. So now we begin the initializing functions. So init, and then we said that it's going to take in the clean function that we mentioned, and it's also going to be a double pointer. So here, the first thing I'm going to do is really to create a list structure and then return it. So let's just go ahead and then do that. So list, I'll call it list, and then we are going to uh, just say malloc size of lst. All right, so we are trying to allocate memory for the new list that we are trying to create. Okay, so let's check for some errors. So if the list that we're trying to create is equal to now, then we are going to um, say that something went wrong. Okay, so here we just say that um, fprintf, we are trying to print the standard error, and then you say that error um, okay, error, and then let's say list initialization failed. List initialization failed. Okay, so here we have the option to exit them out completely from the application, or we can return now, just so that they can make further decisions as to whether they would like to do something else or any other thing, right? Just so that we don't exit out on them immediately. So we will rather return now. So it will be on them to ensure that they are checking for now when this function returns, right? But if everything goes well, then what we want to do is we want to set the size of the list to the size of the list to 0. Then you'd also set the head to now for the first time. The lists, the tail is also going to be now in the beginning, and then the cleanup function is also going to be equal to the cleanup function that they give us, right? So you can see that we have this over here. So that's what we are trying to set up. So we are basically initializing the members of the list that we just created. Then after everything is okay, we are going to return the list that we've just created at this point. So we are going to have the list set, sorry, the size set to 0, the head and the tail set to um, now, because at that point there's nothing in the linked list. And then the cleanup function is also going to be set to cleanup. Okay, so we are going to see how we are going to use this function, and the user is at liberty to provide now, and there's a way that we are going to ensure that in case they provide now, we are going to um, use it well or use a different function to handle that. Okay, so now we have the function that is going to initialize the linked lists. Let's go ahead and then create the function that is supposed to handle the freeing. Right, so this yeah, Patrick.
Ah, okay, okay. So now that I'm back, I actually see why you I actually see why you did not pass in pointer to the list, because you actually it's basically the same thing, because you were, what do you call it, allocating memory for the list inside the initialization function.
Yes, that's
Yes,
all.
yes,
Step by step.
that's great. That's great. I actually think this is a cool way to do it.
Right. Yeah.
Yeah, because I think for me, I don't allocate memory for the list inside the initialization function.
Okay. Okay.
So I
Yeah.
think this is cool.
Sure. Sure.
This is cool. I beg, yeah, share money.
All right. So the next function is to create the free function. So for this one, what it does is that it wraps itself around the original free function. So the difference in this is that we are going to ensure that anytime we are going to free the pointer to a specific memory, we check whether it is already now or not before we do anything of that sort. And once we are done, we set it to now. So this, in a way, is going to help us prevent dangling pointers, which will cause us to maybe do double freeze that we see some errors of those things. All right. So for this video, I probably wouldn't go much into that, but I'll provide the link to the blog that I mentioned, just so that it can explain more of that. So here, the first thing we'll do is to check if the pointer that we are working with is null or not null. So we just say if the pointer is equal to now, or the so we learned pointers the other day, right? So here we are talking about the pointer as in the pointer to the pointer that we are looking at. We check if that is not now, and the dereference pointer. So that dereference pointer is the actual thing that we are working with, right? So we learned pointers, and so I wouldn't go much into that at this point. So we're just trying to ensure that this thing is valid before we do anything. And I find people trying to maybe do something like this rather. Maybe they will do if this pointer is equal to now and this, right? This may look harmless, but then you might have an issue when you do something like this. You dereference the pointer. So think of it in this way: you should never dereference a now pointer. So here, since we don't know whether the pointer itself, it's like the pointer to the pointer itself is not now, and you're dereferencing at this point, you're going to have an issue. So it's always advisable to first of all check the pointer itself, whether it's now before you dereference it. Okay, so um, that's just something I like to just mention. So now that we are sure that this pointer here is not now, then we can free the pointer, then set this pointer to now. Right? That's all this function is going to do. It's going to use the original free function to free memory, as well as right after it is done, it's going to set it to now. So it's going to set the actual pointer to now. So this way, even if we free that pointer again, if you call this function multiple times, we can be sure that we are not going to receive the double free error that we normally see when we
network yangu. Dambe na mimi. Abezanga mikasamba ya.
the first thing that I'll propose that we do is to check if the list itself is initialized. So let's check that. So if the list is equal to now, then you will just tell the person that, oh, well, there's an error. The list is not initialized. All right. So then you just return. Okay. So that's what I was saying. At this point, you could have done something like you could say that maybe here is going to be an integer and then you return -1 or something like that. But here we are going to return um, nothing, but then we will print an error message to tell them that something went wrong. And I think I should also set this correctly. Yes. So when the list is not initialized, we are going to um, back at them and then tell them that, well, the list that you gave me is not initialized. Okay, well, if that doesn't happen to be the case, then we're going to have our new node created. And since we would like to compile with um, the GNU 89, I'll have to bring in my new node at the top side so that I wouldn't have issues when compiling. So I'll create a new node, basically to declare a new node. So when everything goes well and there's like the list is initialized, then I can go ahead and then see that the new node is equal to, let's say, I would have to allocate money for that, which will be the size of a node t. And then you can see how this one is going. We are creating a new node, so we are using the node structure. Okay. So then after we do this, we would also have to check again and confirm that the new node or the allocation for the memory for the new node was successful. If it wasn't successful, you print an error message to them again and then say that, well, error, let's say, um, creation of new node failed, unless the
Offline.
So that's the same thing that we have in the like on the whiteboard, right? So set the next pointer of the new node to the current head, and then we set the head to the new node, and that's what we just did. And also we saw that as we build out this new node that I created, right? So we set the next field to the previous head that we had, and then we set the head pointer to the new node, right? And that's the translation of this same thing into the code, right? And after we are done here, you have to increment our size. Okay, so that's where the size comes in. Okay, so after we've inserted anything, we increment the size, then we move ahead. Okay, so looking at this function over here, do you have any questions on it? Is it okay with you? Do you understand why we are doing this, or is there anything that you like to point out? Anyone? Okay. So I guess for the silence, means that everyone is okay. So we will move forward. Okay. So we will write one more function, and then we would test it out. Then probably check out the other things we can do maybe next time. So let's also go ahead and then write the function for the append method, the append function. So it's going to be similar to that of the push function. That's going to be a little bit different. And that is going to be the case where we are inserting at the end of the linked list. All right. So when we are inserting at the end of the linked list, this is all we do. We like the usual way that we normally do is we traverse all the way to the end of the linked list, then we adjust the tail pointers. But then since we already keep the tail pointers, what they're going to do is going to be straightforward. We just say that we set the new node's next pointer to now because it's the new end of the list, right? And then we set the next pointer of the tail to the new node. Then we set the tail to the new node, right? So let's visualize this a bit so that it becomes simpler. So here, this is our current tail, right? This is where the current tail is pointing to. Now let's say that we have a new node that we would like to insert into the linked list. So here I have a new node. All right. So here the first thing that we can do is to set the next field to now because this is going to be the last list, sorry, the last node in our linked list because we are inserting or we are appending to the linked list. So let's say here the data field was 34. Hopefully I don't have okay, I have 34 already. Let me use 7 something like this. Okay, that's fine. Okay, and then let's assume that this over here received something around 10 that asset address. Okay, so per our pseudocode here, we have to set the new node's next pointer to now, and that's what we just did. Then we set the next pointer of the tail to the new node. So what I mean here is that For the current tail that we have, we would have to set its next pointer to point to the new node. Okay. So before Friday, the one thing I missed out here was the plus one. So after we insert, we see that we increment. So back to here. So we have to set the next pointer of the current tail or the current end of the list to point to the new node, which is going to be the current or the new end of the list. Okay, so this is really what we have to do. We just say that, okay, well, now the next field over here is going to point to the new node, right? Basically, we are pointing to the address, right? So the next field is going to point to this address. So here we can go ahead and then say that the next field here is going to point to that. And then the next thing we do is we say that the tail now points to this node. Okay, so now the previous tail that we saw is not going to point to this one here. Okay, so here we are not doing the operation of traversing all the way to the end of the list. Currently, we have 1, 2, 3, 4, 5, 6, 7 nodes, right? So per the usual method, we would have had to traverse all the way to the end of this list here before we could have adjusted the links. But since we are already keeping the tail pointers, all that we needed to do was to adjust the tail pointers, and then that was all that we needed to do. Okay, so the code for that is similar to this, right? We just set the new node's next pointer to now, then we set the current tails next to the new node, as we just saw over here. Then we set the tail to the new node. It's similar to what we did with the insertion at the beginning, just a little bit different. And also, we also have to check for when the list is empty. So when we are inserting at the beginning or at the end, we have to check for that. Okay, so let's do this as well. Okay, so this is really going to be equivalent, almost equivalent to the push function. So what I'll do is I'll copy this over here, and then I'll just paste it here. Then the only thing I'll do is to just change the function because the function is going to be almost the same, right? With just a few details that is going to change. Everything from here all the way here is going to be the same, except the fact that we said that we are going to set the, so you have to do something different here. The new thing that different is this, that we set the current tails next to the new node, and then we set the current tail to the new node. That's really everything that we are going to do at this point. So we just say that the list tail next is equal to the new node, and then we point the tail to the new node. All right. Everything else stays the same. Then we increment the size of the linked list. Okay, so this is really like with the push and then the append. All right, so you see that here we are not doing any traversal to insert anything into the linked list. It is all happening in what we would say is constant time. It doesn't depend on the size of the linked list. We insert immediately after we create the node. We don't have to traverse anything. All right, so here we um, dealt with the time complexity of O of n, which is the default for inserting at the end of a linked list. All right, so we've been able to cover this particular point. But up to this point here, with the push and then our pen, do you have any questions for how these functions are working? Anyone or anything that you'd also like to share?
Things are clear from my side.
All right. That's good. I know Ahmed says that he wouldn't be able to talk much. Patrick, how about you? Okay, that's great. Okay,
Yeah,
all right. So now,
I'm also okay,
oh,
Maxwell. Just continue. I'm following up.
all right. Okay, okay, that's good. All right. So, um, we've created the push and then the append. Okay. So what I like to do is to let's write a function, or let's say a driver code that is going to um, uh, test what we've done so far, just so that we can see what we've done so far before maybe if anything else we can add it up. Okay, so what I'll do here is I'll create a main.c file which is going to test our code. Right, so vi main.c. So basically, I'm typing or creating a file right from within vi. So you can see down here that I'm doing vi main.c. So that's what I'm going to do. So I'm going to include the list.h. Then let's have our int main function. Then really it's going to look something like what we have here, right? Where we initialize the linked list, then we just insert a few things over here. We are just going to do something similar to this here, right? So um, I'll probably copy this and paste there just to make it easier because it's going to be some data for us to work with. Okay, so now what we will do is this. We said that we will initialize the data. So let me put, uh, okay, hey, okay, looks like it means. Okay, all right. Let's go ahead and then do this here. I think I protected it, so mm, nope, not a good idea. So let's go ahead and then do that one more time. So here the initializer function is going to come in. So we are going to create the linked lists. So we have to say is equal to the init function. And remember that we said that we would have to pass in the the function that we created, which is the free, right? So the user could also say now, and that's also fine. But here we've already created the free function. That means that if they put now, it means that they don't have a function that they've created themselves. So for that, we can use one that we would use for them. Okay, so that's how it would go. Okay, so now that we've done this, again, we would have to check that if the list we received was valid, right? So then we can do something. If it is equal to now, then we just exit out of here, right? So that's what we are going to do. So we exit out with exit failure. That's it. What is going to happen is we are going to just do some few pushes and few appends. So here, just so that we see what is happening, first of all, let's test only the push method. So let's say push, and also as part of this, we are going to be printing the lists for some time. So pardon me, let me just write a function that will print the list real quick, and yes. Because I've been on Samsung's like most of the time to do a function like that. So I just want to do what I said. Okay, so
Yeah.
quickly, yeah. All right, so let me just go ahead and then create that function real quick. Okay, so I'll go into the extras. All right, that's where we're going to create the functions that are not directly associated or related to linked list stuff like the primary purpose of a linked list. So let's go ahead and then create that real quick. So we are just going to traverse through the linked list and print it. So for this kind of operation here, we can't do constant time because we have to go through the whole list. Okay, so now what we will do is we would first of all check if the list is valid. Right, so we say if the list is equal to now here, then we can see that we print out. So at this point, you can see that like the list is not initialized, and I can see myself repeating some code here. Maybe another time or later we can find a way to modularize it so that we don't have to repeat, as well as keeping it dry. I see that I keep checking for whether the list is now and then doing a few things. So we could have a function that will do all of these checks so that I can just call it once every time. So for now, I'll just do that. So if the list is now, then that means that it has not been initialized. But if it is initialized to, there's one more thing that we have to check. If it is initialized, we also have to check if the size is equal to 0. If the size is 0, then you can see that, well, the size is empty. Okay, so we can just say that like, the list is empty, and that's what it's going to be. Right. So if the list is not empty, then you can go ahead and then do something. And again, since you're going to be using the 89 version, I'll create my temporary variable over here just so that we can work with that. So here, then I'll set the temp to be the current head, just so that whatever I do here doesn't affect the head pointer itself. So now, while the temp is not equal to now, we're going to print the data, and yeah, so yeah, so let's just create that. I was thinking of also adding the address of the node, but I think I'll leave that out. So that's going to be D, and then the temp data, then temp equal to temp next, so that we can move to the next node and continue from that side. So that should be everything for the printing of the lists. So I'll get back to the main file. Okay, so let's go ahead and then add a few things. So first of all, I'll just push just 5 into the list. Yeah, something.
Maybe you can go on and also print the address, just for the sake of showing the non-contiguous property.
Right, right. All right, so I'll do just that. Okay, so see that, and okay, that's going to be the 10. Okay. Just to confirm, right? Yeah, I guess that's how it's supposed to be. It sometimes misses me. Either it's supposed to be this way or that way, right? We are trying to print the address of the current node, right? And this is the like the like that. So I guess you would have to get the address in this way, or this way would suffice.
Maybe show the. Let me see the structure, how we defined it. And
All right, so there's a structure.
for that one, we had a head. Maybe can we just print the temp, because at the moment it will be pointing at the list head.
Yeah. Okay, sure. Okay, so we'll keep that, and then let me close out of that. Okay, so let's print the list at this point. So we've just inserted just value 5. So let's see how this is going to print out. So within VI, I can just also open up my terminal just for the ease of working with it. So here I would um, also do that. And as a very lazy person, what I've done is I've aliased the full command to just C. So yeah, whenever you see me typing C, that's what it is. The GCC with all the flags that we are trying to use. I'm just lazy sometimes. Okay, so here I'm going to compile the main.c file and the extras and then the list operations. But since everything here that I'm trying to do is the C file, what I'll do is I'll say I'm compiling all the C files and I'll just save it into the file called list. And yes, there's an issue. Okay, yeah, so I should have called this lists. Yeah, all right, so that's the issue here. You see that here I called it list, but then I was just using list. So that was the issue here that was happening. So now it compiles without issues. Let's check it out. Yeah. So you can see that the thing like was pushed correctly and it was added fine. We also see the address that was given. So let's go ahead and then let's say push a few things. So I'll copy this for some time and then maybe add 10 and then here I'll say 0. Right. So here, what do we expect that would be the return when we print this out? Is it going to be 5, 10, 0? Since that's the order that we are putting it in, or 10, 5, 0, or 0, 10, 5, or 5. Like what's going to be the expected output when we print this out? How is it going to be uh, printed out? Remember that the push function is adding to the beginning of it.
I think that's a
Yeah,
good
anyway.
question. Okay, just to ensure the conversation is there. As we keep on
Yeah.
pushing, what about our head? What is it keeping track of? Will it be at the last function, or will just be pointing to the first element?
You mean the head?
Yes, yes.
Well,
Remember the head.
like yes. So like that, the whole idea of the head pointer is to always point to the beginning of the linked list.
So if that is the case, maybe uh, remember when we were trying to print, we were initializing the temporary to the head.
Yes.
So that does mean that we are starting with the head, and
Yeah.
maybe
So
not.
yeah. Yeah. So I was actually asking that since we are printing from the head, what is it going to be like? What's the output? Since we've added 5, 10, and 0, like how is our list going to look like when we print it? Like, what's the order in which it's going to come out?
Let me try. Maybe 5, 10, 0.
5, 10, 0. Like in that
Yes.
order. All right. Okay. Ahmed, are you? Yeah, can you say something now?
Okay, actually, I didn't get your question, but then I think also the output will be 510. If the head always is always going to point to the first number, I think that's what you are saying, right?
Not exactly. I mean that the head is always going to point to the beginning of the list.
So the beginning of the list generally in layman's time that means like the first number, right? Sorry, I can't hear you.
Yeah.
Sorry, pardon about that. I think you are breaking.
So the first number doesn't necessarily count. Am I audible? Can anyone else know my if my
Okay.
network is very bad at this point?
Yeah. Okay. I wanted to ask: is it only me, or can you also feel it that he's breaking Samson?
Yes, yes, his voice was breaking.
Yeah. Okay. So
Oh,
pardon what
sorry.
you're saying.
All right, can you hear me now?
Yeah. 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 Sure.
All right. So, you see, when we were talking about it, I was saying that you see the link list over here, right?
Mm-hmm.
The head its duty is always pointing to the beginning of the link list.
Okay.
So whenever we push into the link list,
Mm-hmm.
whatever was pushed last
Mm-hmm.
is what the head is going to point to. So it's just a matter of us always saying that the head is always the beginning of the link list.
Okay.
So the fact that we yes something.
Oh, just carry on. Just carry on.
Okay.
I will contribute. I just remembered something.
Okay. All right. So you see the fact that we have it in this order
Mm-hmm.
doesn't mean that like or doesn't necessarily mean that that's how it's going to be brought out when we print it out. Right. So here I'm just trying to see how you get the concept of us pushing to the beginning of the linked list. Okay, so if we are pushing to the beginning of the linked list and we push 5, 10, and 0, remember that every time we are pushing, we are inserting at the beginning of the linked list. So I also made an example of that with this here. So if we have a new node and we are going to insert it, the head is going to point to that node as the beginning. All right. So something you wanted to add something.
You know, I just remembered when I was giving my suggestion from 5, 10, 0, I was basing my answers to just the pointer and the head. I didn't remember we were talking about the push function. Yeah, that's the mistake I made in the
Uh,
first place. Yeah.
all right. Yeah, no problem. Yeah, Ahmed, I see your answer.
Yeah. Okay. So can you try going back to the code so that I think now I get the concept. Then I'll tell you. Okay. So I think the output will be, since the first number to be pushed is 5. The head will first point to 5, then 10 0. So after printing, I think it will be 0 10 5. So I don't think. Uh,
Everything fine.
yeah.
All right. Something, do you think so?
Uh, because our function is pushing to the beginning of the linked list, and the time we were trying to print it, and we have initialized our temporary pointer to the linked the list head, so it will be printing from the last element that is pushed in, which is at the moment is 0. Then the next one will be 10, 5.
But
Yes.
the question you asked me, you see, I didn't really get it. You said that the numbers that you are pushing, you want to know the order in which they are printed out.
Yeah. So I was asking that now we've pushed some few things into our linked list, right? And we are trying to print it out. So based on the function's duty, um, or based on how the function works, how do we think that the list is looking at this particular point? Right, since we're going to print it out. So if we should print this list at this point, what is going to be the result? Like, how is it going to be laid out? Do you get that one now? Oh, okay. I see Patrick is maybe new to at this point. Okay, so let's find out. And I think Samson and Ahmed are on point. Okay, sorry, 5, just as it's supposed to be. Okay, so now we see that also the addresses are not really, let's say, what we may say is um, like contiguous like that much. We can see that here we have the this is the first one that went into the list. Right? We have it
Boss,
in four.
uh, sorry. In my what do you call what? My Wi-Fi with the message.
Uh,
So, do you have a question answer there?
yeah, I think that like we've seen the result of the question. It's going to be 0, 10, and 5 because based on the thing that entered
I
last.
don't, I don't see from my side, but my internet the message.
Probably you can try it rejoin maybe. Yeah.
So, come like I did do something, so I just
Hundred and
have
ten.
the headset on and listening. So I'm not really looking at it. So I just came back to the screen and I don't see anything, but I can hear you clearly.
Okay. I think probably it will just have to do maybe with a quick refresh and it will show. I think Ahmed and Samson you can still see the screen.
Sure, sure. I can see the screen and the output very well.
Okay, good. Yeah, so I think Patrick would have to check his side. All right, so we can again see that this is what is showing up, and this is going to be helpful when we are talking about stacks, right? Like the thing that is happening now, right? We see that whenever we are pushing to the list, we are always inserting at the beginning, right? So whatever we inserted last is the first thing we would see when we print it out. Okay, so now we see that our push function is working all right since it is always inserting at the beginning of the linked list. Okay, so let's go ahead and then try something new that we are going to try to append something to the end of the linked list. So let's say I'm trying to append 25 to the list, right? So now if I should compile this and also print it out, what then is going to be our output? We saw that when we append, we are inserting at the end of the linked list. So
Okay.
also remember that we are keeping the address of the tail node, right? So, but don't worry about all those details. That we are inserting at the end of the list, or we are appending to the list. So based on our current result, this is the current result that we are to expect.
Okay. Okay. So print.
Okay.
Okay. Okay. So okay. So okay. Can you please pardon? You're breaking.
Oh, sorry. Um, I
I
was
also
asking.
didn't hear. I also didn't hear. Really.
Oh, that's right. Okay, so I was asking that now we've added one more code, which is the append.
Yeah.
Right. So I'm asking that if I should compile this code and run it, what output are we expecting that we would get? Yes, Amir.
Okay. I think the output will be starting with 5, 0, 10, 5, and then lastly 25. Because the append functions normally adds an element to the end of the list. Yeah.
Nice. Nice. Okay. Samson, you think same?
Yes, I agree with him. Since we our push is to put at the beginning, then append at the end. So definitely, the last element that we pushed was 0, then 10, then 5, then that we appended to the last part of the list is 25. So 0, 10, 5, 25.
Right. Okay. So we see that,
Yeah.
and it looks good as well, right? So you can see that like we are getting the things as we expect it to be. And here, I'm sort of a little bit. I like to try this. Like I just want to see. You see, like this particular thing. Sometimes it really conf like Excuse me. Either we are trying to do this or that, right? We are trying to get the address of that. For now, let me just try to like, let's say, try this out quickly, because from what I see here, we can see the address is all right, but let's see if it doesn't cause an error. But I'm just trying to feed my curiosity over here. Yeah, okay.
2025.
Now it should actually be the one that we had. Right. So dereferencing the temp is not the right way.
Yes,
So,
because you are doing a you're trying to get the address of the pointer actually.
yes, yes,
Yes.
yeah, yeah, yeah. Uh-huh. It was just something that was sort of just on my mind, and I just wanted to clear it up. Yes, Ahmed, I see your hands up.
Okay, okay, so I have a small question. Okay, so what if in a situation now I want to add maybe an element between 10 and 5? Which function am I supposed to use?
All right, so that's why we are going to use this function called insert at. Right.
Okay, okay,
To, we are here to write those functions. But then, first of all, I wanted to establish the fact that we are able to insert at the beginning and at the end without having to traverse, right? Because mostly when we're inserting at the end of the linked list, right, it's going to be, let's assume that the size of the linked list is very big. We'd have to traverse all the way to the end, and that's not a very good thing to do. So that's why this method is a bit better, and also it's going to be very useful when we are dealing with queues and stacks, queues especially. Okay, so now also, yes, Samson.
Uh, Maybe can we also try and you see for the append message function, if you can try and mix it with push rather than maybe aligning it with maybe after pushing yes a number of them then append, what kind of output are we expecting? Let's see.
All right, sure, no problem,
Yes. And you can even append after the first two push.
no problem. All right, so let's do an append of, let's say, 100. All right, so we have push 5, 10, append 100, push 0, append 25, push 98, push negative 34. I think the pushes are too much. And okay, let me add one extra append. Let's append this. Let's see. Let's append. Boy. Okay, just some random number. Okay, so that. Okay, so let's think through this as well. Yeah, push 5, push 10, append 100, push 0, like that. So um, what are we expecting that we are going to get if we should try this out?
okay,
So let's go. We see that. Okay, I think I would. I'm sure. I'm sure. Maybe you guys are already trying to put it put it together. Well, let's see. Has anyone been able to work it out so far?
okay, maybe,
Maybe before you compile it, maybe you can try and give our suggestions. So can go around the members.
yeah, okay.
Yeah. So
Le-
could you repeat that? I think I didn't catch that well.
okay, 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 let me, Maxwell, Samson was saying, so before you compile the code and so that we can see the output, we should first try maybe guessing the output. So
Yeah, yeah,
so I think
yeah.
because Samson is
That's
the one who,
actually,
okay, okay, sorry. Oh, just continue,
sorry,
just continue.
sorry. Oh, sorry. Yeah, so I was actually asking if anyone has been able to figure out how it's going to be. Right. So I was actually going to, like, I was asking how someone has actually figured it out, or like how they think it will be, and then we write it out over here,
For 100.
then we compile, then we check. All right. So I was asking if anyone has been able to figure it out so far. Yeah.
Maybe I can try.
Okay.
Uh,
Sure.
I can start with the pushes. So the last push was negative 34,
Negative
and
34.
then 98,
98.
and then the other one is 0,
0.
10,
10.
and then 5. I think there are 4, right? How many are they? 5.
Yes.
1, 2, 3, 4. Yes. Then the first append was 100, so that's what I'm going to add.
100.
And then 25,
Then 25.
then 93, 83.
93. 83.
They're just
Right.
3.
Yes. For the append, actually. Yeah.
Okay, okay.
Yeah. So this is from Samson. Anyone with a same answer or a different answer?
Okay, maybe.
Yeah, I mean, please go ahead.
Okay, okay. I think I'll agree with Samson on this one, cause since we start with the push, since the head normally pushes to the yeah, so I think we'll start with also negative. I think I'll just go with Samson. Negative 38, then 98, 0, 10, 5, then with the append, which is 100, and then 25, and then 93, 83. So I think I'll go with Samson there.
All right. Okay. That's good. And actually, particularly like how he's like broke it down into the pushes and append, right? Because I was actually looking out for like that kind of way of doing it because it would have been hard to try to do the pushes and the appending, like putting them together like that. So I think it was a nice approach to look at the last push and work your way through that, and then add the appends. That was a very great way to do it. I think Patrick is still with us, or if he has a different answer.
Mark.
Yes.
Okay, so can modifications be made for if you want to push, let's say, push or append, let's say, integers or let's say numbers and also strings.
Sasa ukiona iko na scratch hivi, hiyo ni network.
Didn't
Hiyo
catch
ni
that well.
YouTube ndio iko na scratch hivi. Sasa huwezi toa.
Okay, so what I actually wanted to ask is
Kama
that
una
can
kama una
modifications
message
be
namba
made
yake.
to accommodate when you want to, let's say, push numbers or say
Kama pale
integers and then
hizo
strings or let's say words
downloading
on
lines
into the same list?
mwenye aliweka left.
Yeah,
Actually
it's actually possible to
labda sasa
contain
kuna
Yeah.
different data types.
ingine tena. Sasa
Yeah.
si rahisi.
Yeah. So I was actually
Hiyo ndio huwezi toa.
asking because
Sasa
I did it in a different way. So I actually wanted to know how
kama
you
Musa alikuwa
also
anataka na
implement
scratch.
such if you wanted to
Nilikuwa
do
na
that.
scratch na inafaa ikuwe niko hapa
Okay.
pembeni.
But for now, we are asking how this will look like.
Hapa
We
mwanzo
can
mwanzo
discuss that
taa. Hapa ni mwanzo
maybe
mwanzo hapa
another
taa.
time. But you were
Vitu vyote
asking about, let's say, if we have this data here,
ukiona
uh,
scratch hapo mwanzo
based on
mwanzo
this
taa.
the append methods,
Usilikubali hivi.
like
Okay.
saying that
Upost kitu
our
hapo.
result is going
Kama
to
kwanza
be.
kuna mahali unaituma inaangaliwa alafu ndio inakuja.
Yeah.
Huwezi tuma direct.
And Samson and Ahmed are agreeing that it's going to be in this format
Sasa
here.
mimi hapo
Right.
nenda ngapi?
So
Hapo naweza pata ndio nusu sana.
I don't know if you agree with them or you think different.
Ngaka mpika hiyo mix ya jina mata.
Okay. So let's say
Body
we have
mwenye
five,
alirekodi.
push 10, and
Body mwenye
append 100, push 0,
hiyo
append
mix
25, push 10,
anaweza
push
angalia.
98,
Yaani kama alirekodi
append
mix. Sasa
900
yote si hiyo
and
wimbo. Ama wewe mwenyewe kama
9,783,
wewe.
and push.
Ama mna push huku YouTube. Wale wamekubali kusema
Well,
version wanataka
we are pushing
prevent on YouTube.
at the beginning of the
Inaenda
list,
kidogo na
right? And
asipana
then
Yeah.
for
nilikuwa na
appending, the appending is actually done at the end, yeah.
kaa kwa nusu tano.
Yeah.
Good. So I think for that one, if we are pushing like we push five, and then we would actually
Lakini alikuwa
let me
amerudia
see.
niende, alikuwa amerudia niende mawili pia yeye.
So
Sasa nikakata
okay, so it's
tatu
actually
nikamwambia
going to
nikuwa
be
na
like this. We would
nikifika
have
hapo natoka nikicontinue.
let me see, 100.
100.
So let me go to the
Okay, hapo
points.
sawa. Nikakata hivyo.
So,
You clear the 100 first.
all right,
Mhm. And then let's push five.
push 5,
Then
then
zero,
0,
um, 98,
98,
and then minus 34. Yeah,
34.
good. So that would mean that, and let's say that if we pushed 5 and
Na
10,
nimekata.
and then we did an append, right? So from 5 and 10, oh, so for 5 and 10,
Hmm?
we did an append, and then
Island nimechelewa nimefika. Nilikuwa tumeenda mahali ingine mbali.
Patrick.
Tumetoka mbali huko. Eh?
Okay. I think Patrick is lost for a while, but I think he's going in a direction where he might put himself in a very tight corner. So, yeah. So, yeah, Ahmed, please.
Okay. Okay, I wanted to say so that Patrick has already left. I wanted you to tell Patrick what how okay, he's back. So I wanted you to tell Patrick on how the node actually works so that he can rectify the output he was giving.
Uh,
I think that's the place he's not getting clearly.
yeah, let me just bring that back. All right.
well, well, actually, how I wanted to do is that that's basically the style house. That's how I do. Like I first of all, like when I'm looking at it like this, I first of all think about it in pushes first, and then when I have all the pushes, I start to what insert the appends, and
Yeah.
that style always works for me because it makes things more clear for me.
Yeah. Okay. Sure. So, okay. So we have
So
the.
I think my style might be like unconventional or somehow weird, but I mean to each his own, right?
Yeah, we like weird here. So currently you said 5, 10, 0, 98, negative 34. There are, okay, I think we lost him one again. Okay. So probably I think we should go through this one more time. So I'll just leave the answer that
Sasa niangalie
he
hii
gave, right?
niangalie
So
nimesema
we see that we did a but we did multiple pushes and then
prof okay.
at each push we also do some append sorry,
No.
push and append, right? And here we are not inserting within the list, we are inserting at the end or at the beginning. Okay, so um here we said that every time we push we are inserting at the beginning of the list, and every time we append, we are inserting at the end of the list. Okay, so um, here we have two um, outputs here, which Patrick couldn't finish because I think his network is not stable. It keeps hesitating out and bringing it in. So um, what we'll do is let's compile this and then let's look at the result that we are going to get. Right, the result is actually going to be okay. Well, let the result speak for itself. Okay, so let's go ahead and then do that. Okay, so we
Okay,
see that we
iko
have negative 34,
98
98,
0
0, 10, 5,
5 10
100, 25
25,
93
93.
9 sorry 9383.
Exactly.
Okay, and that's what Samson and Ahmed agreed to. Okay, so the thing here, like that's what I was saying, that also Patrick, right? It's a good thing that you are saying that you grouped the pushes first, and then you would also group the append, right? But then the order in which you are saying it is what we are looking for. So every time we push, we are inserting at the beginning of the list, and every time we append, it's going to the end of the list. So that's the order that we were actually looking for.
Um, Mark,
Yes.
Mark,
Yeah, I can hear you.
uh-huh. You are saying
Wengi
the
wamefunga
order you are
room.
looking for.
Siku hizi napika 3/4. Naacha kupika kitu moja.
Yeah, so I'm saying that you see, with a push function, it's going to always
Wewe
insert at the
3/4 watu
beginning of the
wanalala
list,
na njaa eh?
and the append is going
Ama
to
ni mimi
assert,
huwa nikipiga hii
sorry, insert
breakfast.
at the end of the list.
Bas.
So
Yes.
Ule huwa hata sipati
every
time ya
time
lunch.
we insert,
Juu
or every time
tunaingia kama
we
ni saa
push,
tatu
we
halafu
are
tuwe
pushing it at the beginning of the
lunch
list,
venyewe.
and
Yes.
we append, it goes to the end.
Nikipiga
Right.
hapa breakfast
So
yangu ndio
Yes.
usikose.
it actually means that
Hata heri niweke
the last
mafuta
push we
hivi.
do is going to be the first element in the list. Right.
Yeah.
Yeah.
Hai.
And
Sasa
the first
nikikufukuza hiyo
append
siwezi
we do
kukufukuzia
is going to
siwezi.
be the like if
Toa kamera kidogo.
or like the last append we do is going to be the last element. Right. So the first, sorry, the last push is going to be the first element, and the last append that we also have is also going to be the last element. Okay. So like when you're looking at it this way, you're looking at it from, okay, what was pushed, and if I'm trying to get it back, how would it be like? Right? So we are pushing in the order of, let's say, this. So probably we're not discussing stack, but like every time we are pushing, we are putting in into the list in that way. So um, we push something, it goes in there. We push another thing, it goes there, like in that order. So the last thing that, or the first thing that we push is always going to be at the bottom, and the last thing we push is going to be at the first position. So that's how like the pushing is working. But whenever we are appending, we are always inserting at the top. We are not like okay. I think I missed what I was trying to say. Let me rephrase that. Whenever we are pushing, we are always inserting at the beginning of the linked list. Right. So let me rather use this. Right? So when we are pushing, we are always creating a linked list like this. Then we set the current head like this over here. We set it to the new node. Then we set the head to the current one like that. So every time we push, we are inserting at the beginning of the linked list. All right. So and also when, oh boy, when did this happen? Um,
Mm.
Give me a moment, please.
Hata vitu vingi. Hata hii hapa.
Okay. So you
Hii
see, when
aka
we
kamoja kahuyu ni
talked
character.
about the push function, we said that we are always going to be inserting at the beginning of the list, and then our pen is going to be at the end. So
Depend
by this way,
anafaa
if you're trying to
kumaanisha
figure out
kitu
the
hiyo.
order in which it's going to be, you would have to do like know the number of pushes that we did. All right. So based on the number of pushes that we did, you can also figure out the order in which the pushes are going to be. And the appends that we also did, you can see that always the append is going to insert at the end of the list. So if we know how the pushes ended, then we can just add the appends at the end of it. Right. So I think we lost him one more time, but I hope it's clear to all of us here so far.
Yes. Ah, this is
Okay.
pretty clear.
So okay, that's great. All right. So we've seen these two things so far, and I guess I mean our time is, let's say, fast spent, right? Yeah, yeah. So maybe if we would end here, or since you are our senior boss over here, regardless, right? So, what do you think we should do? Uh, we've gone actually past the um,
Okay.
threshold that we set for ourselves.
Okay. Actually, I think okay. Normally, this session should be lasting for 2 hours. We only give them an hour depending on the host. So, but then the time allocated for each session is normally 2 hours. So far, we have used 1 hour. I think 1 hour 53 minutes. So, I think 6 minutes remaining so that we can finish the session. So,
All right, no problem.
so just finish up on what you wanted to say, and maybe on Monday you can finish up on what is remaining, unless anyone else has something to say on that. Okay, Samson.
All right, yeah, sounds good.
Yes, I think since we've talked about two operations and exercise on them, the push and then the append, maybe we can
Stop there.
just wrap up things, and
Yeah,
then in our next session we introduce the insert art,
yeah, sure.
then carry on from there.
Right. Okay. So, to wrap things up, right? Okay, yes, I'm in.
Okay. I just wanted to say, a big group has not said anything since he joined. Maybe we should listen to something, or maybe even say hi. Say hi, group.
Hello, everyone.
Hey,
Hello.
hello.
Yeah, hello.
Yeah, I can't let sorry man, but next time I'll try to be early. Yeah, and thank you so much for the good work you're doing. I appreciate you all.
Okay. Maxwell.
All
Yeah.
right.
Okay.
Okay, thank you. Okay, so today we looked at how to create a linked list by keeping the tail and then the head pointers with the aim of being able to insert at the beginning of the list and at the end in constant time, meaning that insertion does not depend on the size of the linked list. Right. So, because the usual way of doing it is that whenever we intend to insert at the end of the linked list, we would have to traverse all the way to the end, which is going to be an expensive operation when the list size grows. So with this, we're able to insert at the head or at the beginning and at the end in constant time. So we also talked about the fact that we needed some few things, which were our initializer functions that would take care of creating the structure or the objects that we would use for the list. So we also saw the structure for the node. We only kept two members in this structure, which is only the data field, which is going to be an integer, and then a next pointer for our structure. So that's how we build linked lists. We use the self referential property of a structure to help us do that. And this is our list structure that we use so that we can keep the head, the tail, and then the size of the linked list. We also kept a function that we use to remove or to clean up nodes when they are being deleted, but we'll see that function in action at a later time. So we also saw how to insert at the beginning and also at the end of the linked list. We said next pointer of the or the next field of the new node to point to the current head that we have if the list is not empty. Then we set the head to the current node. The same also applies for the part where we are inserting at the end. We first of all ensure that the next field of the new node that we are inserting is set to now to ensure that or to say that we are at the end of the list. Then we set the next field of the current tail, which is the end of the list, to the new node that we are trying to append. Then we adjust our tail pointers to point to the new node, which is now the end of the list. Right. So the operation of these two things are almost the same, but just that the position where they are being put is what is different. So with these operations that we are able to do these things in constant time, as opposed to doing the insertion at the end with the what is the normal O of n that we wouldn't like, right? So we also said that whenever the list is empty, we ensure that we are setting the head and tail pointers correctly. That means that when it is empty, we insert at the beginning and the head and tail point to the new node just to ensure that, I mean, it is the very beginning of the linked list. So both of these two things have to point to the same thing. Okay. So with that, we ended with looking at some few driver code that we used. We tested the push and append functions, and we saw that they are working so far. And we were able to confirm our answers. And when we checked, they were also correct. We also wrote a simple function that will print out the lists when we needed it. Right. So essentially, that's what we were able to cover today. Um, Implementing the linked lists, and then working with the push and append functions, as well as the initializer function that we said would create the linked list for our usage. So that is everything that we're talking about today. In the next session, we'll also work with the insert arts, the delete arts, and then the pop function. Hopefully, so that we can insert anywhere in the list, and also remove from the list anywhere that we would want to remove from. But for now, that's everything that we would mention. Maybe in the next session too, we would see how these macros are working, the first and then the last. Okay, so that'll be everything from my side today. Ahmed.
Yeah. Okay, so thank you, Maxwell, for this session, and a big shout out for everyone who has joined. Yeah, so it was a really wonderful session. I've learned a lot. For those who have missed the session, just feel sorry for them. So thank you for the session. So next week we'll continue from insert art, and then you'll finish the rest with the pop, delete art, free, print list, and then I think we'll go to the next host. I'll just DM him since I've not seen him today here. Yeah, so okay, let me first of all end this recording so that I can say something else. But then thank you guys for everyone who has watched up to this point, and follow for more.